All right, today is Thursday, 28 March 2024. And since there's nobody here, no students here taking the exam scheduled for today in person, and I'm going to go ahead and get started on the next topic, which is chapter 13 in your textbook, gases. Now, when you go into Brightspace, you will find in this module, exam number 7, you'll find in this module the PowerPoint slides that I'm going to use today. Plus, you have access to this review document for chapter 13. And there's also a key there for that document. Plus, if you have trouble solving the problems and you need more detailed instruction, then there's this worked problems that parallels the review document. And then, of course, next time we meet, we'll start a review and use this review document. All right. Chapter 13, gases. After chapter 13, we have 2 more, acids and bases, and each one of these chapters is a separate exam. So I have 7, 8, exam 9. And I believe, I'm going to check to be sure. Okay. There is a comprehensive final exam. All right, so you have exam 7, 8, 9, and then a final. And this was a possibility, talking about energy, but the course is not, in other words, there's not enough time to do this chapter also. So we're going to stop at redox reactions, chapter 18. All right, gases. These are the topics that we're going to cover today. And the question naturally is, well, you could ask this question for anything in this course. Why study fill in the blank? Why study gases? Well, actually, there's a good historical reason for studying gases. When when the Renaissance was gaining speed and the rest of Europe was following along, and coming out of the Dark Ages, we had alchemy was what eventually evolved into chemistry. The modern approach to the sciences required that we had, number one, the technology to study phenomena. And the technology for studying gases was fairly well developed at the time a modern scientific investigation was being developed. So historically speaking, the study of gases comes first. And the nice thing about gases is that when we're studying the physical properties of gases, one gas is as good as another. In other words, at the conditions that we experience at, say, room temperature, atmospheric pressure, one gas will act pretty much like another gas, which made the study of gases a little easier. You didn't have to purify a gas in order to study it. And in fact, when the investigations, the scientific investigations started getting going in the beginning of the 17th century, separation of gases was not an easy task if you had a mixture of gases, how do you separate them? So the fact that all gases, whether mixtures or not, behave similarly in their physical approach, and that was the first study. We studied gases. Well, actually, we studied gases physically, we studied gases chemically, but the first scientific advances that were reproducible and reliably defined were physical properties. And then the chemical properties eventually caught up. Okay, and real world phenomena involve gases to a significant extent. And I sort of I danced around this topic, understanding how science works. Gases are an excellent place to start. And then once we have the physical phenomena pretty well in hand, we're going to cover those, the gas laws. Then an understanding of chemistry soon followed. All right, what is a gas? Well, we can characterize a gas as one phase of matter. And one characteristic of a gas is it has an, let's write it this way, indefinite volume. In other words, you put a gas into a container, it's going to expand to fill the container. And you can't hold a gas in a container that's not completely sealed, because it will continue to expand into the universe. Another characteristic of gases, well, indefinite volume, also an indefinite shape. But also, when you mix two or more gases together, you always get a homogeneous mixture. Right? We have a special name for that. It's called a solution. Homogeneous mixture, another name for a homogeneous mixture is the solution, and mixtures of gases always form solutions. Gases also, when confined, we can measure a pressure of that gas inside the container. They exert a pressure on their surroundings. And for our purposes, the surroundings would be the container. But they also exert a pressure, even if the gas is not confined in a container, like the atmosphere, right? It exerts a pressure on me while I'm standing here at 2,500 feet above sea level. Now, if I go down to sea level, the pressure will increase. If I go up, say, to Denver, Colorado, another 2,500 feet up, the pressure will be less. So gases exert a pressure on everything around them. And we're going to investigate why that is before this chapter is finished. So if a gas exerts pressure, we need a way to quantify the pressure, to measure the pressure. And that means we have to define what pressure is. Pressure is a force per unit area. So remember when we were talking about extensive versus intensive properties. An extensive property is one that varies with the amount of substance. And an intensive property is one that does not vary with the amount. Okay, an extensive property would be a force, right? Forces can change. And the force of a 1 kilogram mass in my hand will be less than a one gram mass in my other hand. So the force depends on the amount. Area changes, right, with the amount. An area of this room is more than the area of the tip of my finger. So when you ratio them, you change these two extensive properties into an intensive property. So pressure is the same everywhere. Once measured, as long as we don't change one of these without changing the other, then the pressure will remain constant. It's an intensive property or an intensity factor. Now the units for pressure are, in fact, measuring pressure, pressure has many, many more units of measure available to it than most other measurements. Now, if we take this definition and we use international system units of force and area, then we have the Newton, right? That's the Newton. I think that's the way we spell it. No, sorry, that's a W there, Newton, and square meter. So 1 Newton per square meter is a derived international system unit. And we give that a special value, which is the Pascal. All right. So what is a Newton of force? Right? The square meter is derived from the standard unit of meter, square meter, but the Newton, the force of Newton, is derived from Newton's second law of motion. Right? Newton said that force equals mass times acceleration. Right? So force is what we're after here. So what's mass? Well, the standard for mass is a kilogram. The standard for acceleration is velocity per unit time, and velocity is meters per second. So meters per second changing over the time unit of second. So what we actually have is kilogram meters per second squared. So one of these is equal to 1 Newton. Now, why am I showing you this? Because when you do calculations, if you have a Newton here, or you have a Pascal there, and you put that into a formula that requires a pressure unit, and you have other factors with different units, then how are you going to resolve that calculation? Because if you don't know what a Pascal is equivalent to, there's no way to cancel units. And you don't know if the unit that you end up with is the correct one. So if we put a Pascal into a calculation, maybe we need to have newtons per square meter instead, if there are meters in the calculation that need to be canceled. But also, if you have a Newton per square meter in there, and you have kilograms and you have seconds in your calculation, then those need to be canceled, and you need to equate that with this divided by square meters. See what I mean? So if you know what these are, the equivalencies are, then you can substitute the correct units of measure, and that makes it more likely that you will be able to determine if your calculation is correct. Because just because you get a number out of a calculation doesn't mean it's right. If you also follow the units of measure, then you're more likely to get an accurate calculation, right? So the Pascal is one way of measuring pressure. Or newtons per square meter. Another way to measure it is in terms of atmospheres. Right? At sea level, the average pressure is considered 1 atmosphere. So we have pascals, we have atmospheres, units of measure, and then we have equivalencies for that Pascal that I'm not going to put up there right now. And then we also have an equivalence between the atmospheres and pascals. So 1 atmosphere is equal to 101,325 pascals. Okay. Now, if we want to reduce the size of the number here, right, we could say kilopascals. Right? So if we put a kilo in front of the Pascal, then we need to move the decimal to the left 3 places. 101.325 kilopascals is 1 atmosphere. All right. There are other ways of measuring pressure. Right? 1 atmosphere is also equal to 760 millimeters of mercury in a Torricelli barometer. Right? I'm going to describe that in just a second. So we have these equivalencies, and remember, from the first chapters in this course, what do we have when we have an equivalency? We have a conversion factor. As long as you have an equivalence, you can create a conversion factor. Right? So if I have, say, 6 atmospheres, and I want to convert it to millimeters of mercury, dimensional analysis says that atmospheres must be down there, numerator, denominator, millimeters of mercury. Then the equivalence is 760 of these for one of those. Now we have a conversion factor. Right? So we're not just whistling into the wind by giving you these values. They are useful. Also, this is equal to 760 torr. Torr is a unit that's equivalent to 1 millimeter of mercury, and in honor of the inventor of the mercury barometer. Okay. So I think the next slide also gets into how that barometer works. All right. So how did Torricelli invent his barometer? I mentioned earlier that the technology determines what type of experimentation we can do, right? At the beginning of the, let's see, Torricelli was when? Beginning of the 17th century, okay? Torricelli, well, at this point in time, measuring volume was an established technology. No problem with volume. But we needed a way to measure pressure. Right? We could measure force, right? But we needed a reliable way to measure pressure that was consistent for every scientist who was interested in working with that value. So Torricelli took advantage of the fact that at the beginning of the 17th century, technicians were very good at producing glass of any dimension. So he acquired glass of a certain diameter, and it was uniform diameter. And all he had to do then was fire seal one end of it. So he had this long tube, right? and he filled it with mercury. Now, why use mercury? Well, mercury was a liquid, right? You needed a liquid. Solids wouldn't work. Gases were too hard to confine. Liquid was perfect. But why mercury? Why not use some other liquid that was maybe safer, right? Like water. Well, I'm going to explain to you in a minute why water doesn't work. Oh, it does work, but it's not the best choice. So he filled it with mercury and got all the way to the top with mercury. Then he put his thumb over the end of that glass tube and inverted it and submerged it into a container of mercury. So now it's inverted in that mercury. And when he removed his thumb, guess what happened? The mercury didn't stay at the top. The mercury dropped a certain distance. And at sea level, that distance between here and there is 760 millimeters of mercury. So we measured pressure based upon the height of a column of mercury. And what Torricelli reasoned was, that the height of this mercury, the mass of that mercury, is being supported by an equal force or mass of air above this surface. So the mercury is bearing down here with its own force, and air is bearing down there with its force, and they're balanced. Okay? And since pressure is an intensive property, it doesn't matter how wide that tube is or how big this vat is, right? This force per unit area is the same no matter what. Okay? So it was pressure indeed that was being measured. Now, some interesting facts. If you have matter, any kind of matter in this space, and now you don't, what do you have in that space? You have a vacuum. There's nothing there. Well, actually, there are a few atoms of mercury because it's slightly volatile. But for all intents and purposes, that's a vacuum. Okay? All right, so this was a reliable way to measure pressure. Now for the question of why was mercury used? Okay, why was mercury used? Well, the force required to hold that mercury up was a certain amount, right? And the mass of mercury between here and here is a certain amount. If you need the same mass of water, the column would have to be 13.6 times as high. I think that's 13.6, or maybe it's 13.5. Right? That's because mercury is more dense than water. So the column that air would support, the air pressure would support, was a column of water that would, in effect, be about 33 feet long. That was not convenient. In fact, 33 feet height of water is 1 atmosphere pressure. Right? That's why scuba divers know that when they descend 33 feet in a body of water, that they've added roughly 1 atmosphere pressure on their body. 1 atmosphere from the air, 1 atmosphere from the water, so there are 2 atmospheres on their body. They go down 33 more feet, like 66 or 67 feet, there's another atmosphere. So the deeper you go, the more the pressure. All right. So now we have a reliable way to measure air pressure And other scientists took Torricelli's invention, and Torricelli worked with it also. And some of them, Torricelli included, put their barometer in the back of an ox cart and went up the mountain. And they found that the air pressure at higher elevation was lower. And if they were at a certain elevation and they went down to sea level or below sea level, right, in places like, well, modern places like Death Valley or the Dead Sea, then the height of the mercury column would increase because there's more air above it. And that was confirmation that Torricelli's invention was actually measuring pressure or the height of the air column above the device. Okay. Another way to use the barometer is just let it sit there on your desk. Watch it over time. And you'll notice as the weather gets bad, the pressure drops. As the weather gets good again, pressure goes up. And we still use that today. Low pressure versus high pressure systems of the atmosphere moving through cause the barometer to change its height. And we can predict, based upon that, whether or not we're going to see good or bad weather. All right. So for chemists, though, we can use a modification of Torricelli's invention called the manometer. And what the manometer does is simply measure the pressure of a trapped gas inside a vessel. And here we have two examples, right? If we have this open tube on one end, we have mercury in this part of the tube, and we have a trapped gas here. Then, and we have a separate barometer where we can measure the atmospheric pressure, right? Then we can actually determine the pressure inside that vessel. Because you know you've got one atmosphere pressure here, or whatever the barometer says it is. Then you've got a pressure in here opposing it. And the difference in height of these mercury columns will give you the pressure inside the vessel. What we find with this example on the left is, if this side of the column is higher, that means there's not enough pressure in here to counteract the atmospheric pressure, right? Plus the height of the column. So that means the pressure inside the vessel is less than atmospheric pressure. And if in the other case, we've got more pressure inside here than the atmospheric, that means it'll support atmospheric pressure plus the pressure of the column. So the total pressure is equal to the pressure of the gas plus the pressure of the atmosphere. All right. All right, that's enough for now. Let's not get bogged down in details at this point. So that manometer allows us to measure the pressure of gas inside a confined vessel. And also the medical profession got hold of it and they modified it even further. We call that a sphygmomanometer. And that measures the pressure of your in your circulatory system by putting a cuff around your arm and pressurizing the cuff so that we can watch the pressure change with each beat of the heart. All right, this is what happens to, to a can when we decrease the pressure inside the can and the pressure outside the can remains the same. Right? So how do you decrease the pressure inside that can? Well, first of all, the can on the left has no cap on it, but it does have water. There's water in there. We heat the water. We fill the container with water vapor, right? The gaseous form of water. Then we cap it, turn off the flame, and let it cool. What happens to the water? As the water vapor cools, it turns into a liquid. And what does it leave behind? right? It leaves behind very low pressure water vapor left over inside the container. That's not enough pressure inside the container to counteract atmospheric pressure. So the can reaches its limit of integrity and collapses. That's another demonstration of the reality of atmospheric pressure. All right. So for an example, if we have a gas that's measured at a pressure of 2.5 atmospheres, and we want to represent that as both torr and pascals, so 1 atmosphere can be converted to torr, right? If we use this relationship, 1 atmosphere is 760 torr. And now give us a value. 760 times 2.5 will give us 1.9 times 10 to the third torr, or 1,900 torr, or 1,900 millimeters of mercury. How about pascals? Well, we have an equivalence here of pascals. Let's see, let's use this one. 2.5 atmospheres. And then we have a conversion factor, atmospheres and pascals. And we have 101,325 pascals times 2.5. And now we have 2.5 times, roughly 2.5 times 10 to the 5th. Two significant figures. All right, so let's try another example. The vapor pressure over a beaker of hot water is measured as 656 torr. What's this pressure in atmospheres? Right, 656 torr. Now we need the conversion factor that will change torr to atmospheres. That means torr on the bottom and atmospheres on the top. And we know that 760 goes here and 1's there. So 760 divided into 656 will give us 0.863 atmospheres, less than 1 atmosphere. All right, now we're going to talk about the gas laws. We've got a way of measuring pressure. And Robert Boyle was an Englishman who did many things, right? But he took Torricelli's invention and the concept behind using mercury to measure pressure. And he took it, and instead of a straight tube, he used what we call a J tube. The closed end is a little shorter than the open end. In Boyle's experiment, before we talk about Boyle's experiment, let me give you some more information. If you want to define the physical properties of a gas and how it behaves with changes in those properties, you need to know 4 factors. You need to know the pressure of the gas. You need to know its volume. You need to know its temperature. And you need to know how much of it there is. And this is my abbreviation for moles. N equals moles. Okay. So what Robert Boyle did was he used this curved tube, and he added mercury. So if you put mercury in here, right, then it's going to pool up at the bottom, and you're going to add a little more, pools up a little more. Once it reaches the inside of that curve, and touches the inside of that curve, now all this gas in here is sealed off. Right? In other words, we've established a certain amount of gas in here, right here, and that's constant. The constant number of moles of gas is now sealed in that part of the tube. Okay? And this experiment takes place over a very short period of time. So the temperature is not going to change very much either. So that means this is constant. Okay? If these two are constant, then we can let pressure and volume change and see how they behave against one another. All right. So as he kept adding mercury, what he noticed was he may get mercury up to here, right? Mercury fills that part of the tube, but it'll only go up to here on this side. So what he reasoned was that the trapped gas in here was pushing back against the added height of that mercury. Okay? Now, what's the total pressure on that gas? The total pressure on that gas is this much mercury, right? Millimeters of mercury, plus atmospheric mercury. So the total pressure are these two values. Now, what's the volume inside that part of the tube? The volume is volume equals the height of the tube times the area, the cross-sectional area of that tube. This is a cylinder, right? So what's area? Well, area equals areas pi r squared. Or pi d squared over 4, either one. Well, notice that the area doesn't change. It's the same all the way up and down that tube, right? So volume is proportional to height. So if we're only doing this experiment in a short period of time and confining our results to that one device, then we can use this as an equivalent to volume. All right. So what did Boyle discover? As he added more mercury and the pressure changed, and he measured pressure in terms of atmospheres, right? As pressure changed, volume also changed, right? So each one of these experiments is we get a certain amount of mercury and we have a certain volume, and you multiply the two, right? So you get values here, 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 here. And he noticed that if you multiply pressure times volume, it's equal to a constant. It's within experimental error, the same value all the way down. So that's Boyle's law. And Boyle's law is pressure times volume equals a constant. And that's what this table taken from your textbook shows you. Right? If you measure pressure and volume on a trapped gas and you change the pressure, the volume will decrease. Now, when we graph that, how would we graph that? Pressure is what I am changing as the experimenter, which means it goes on the x-axis. Right? Pressure goes there. And the y-axis is the response. What is the system telling me when I change the pressure? That's the volume. Well, if we put those values in here, then we get a curve like that, which means as the pressure increases, the volume decreases. In math, that's known as a negative slope. The slope is negative. Anywhere on this line, the slope is negative. That is, as x increases, y decreases, or as pressure increases, volume decreases. That's known as an inverse relationship, or proportion. Inverse proportion is graphed like that with a negative slope. Now this is a curve, so it has different slopes, but they're all negative. All right. One thing about scientists is we don't like curves. If we can get a straight line out of our data, that's better. It's easier to deal with. All right, negative slope. All right, so if we let pressure and volume change, we have to have temperature and moles constant. Now, that's not very useful. I mean, it is true, right? That relationship is true, but it's difficult to solve problems with it. So what we've done, mathematically speaking, is to say, well, at this point, we have pressure 1 and volume 1 is equal to K. And at this point, volume 2 is equal to K. Volume 3 is equal to K. Well, what we're saying is this pressure times this volume equals to that constant. And this pressure times this volume is also equal to that constant. And remember that mathematical rule. If A is equal to B and B is equal to C, that means A is equal to C. So we don't need that constant anymore. Now we have this relationship. I call this before and after. This is before and this is after. If you have information that tells you pressure and volume at this point, and you have information that tells you pressure at this point, then you can calculate volume, right? Any equation that has variables in it, and you know the values for all the variables except one, you can solve for that unknown. And this is just an illustration. As you increase the pressure, you decrease the volume. All right, so here's an example. Let's see, let's make some room over here. All right, say we have a sample of helium gas that occupies 12.4 liters at 23 degrees and 0.956 atmospheres. Here's what I suggest that my students do. When you have a word problem, and I've said this before, word problems are designed to confuse. In other words, they have information in them and they have a question. Now, whether or not you need all that information is for you to decide. Maybe you don't need all that information, or maybe there's information that's not in the problem that you need, and you have to go outside and look it up. So I ask my students to say, all right, what type of problem is this? You're given 12.4 liters of gas at 0.956 atmospheres. Is there a change? Yes. The question is, what volume will it occupy if the pressure is 1.2 atmospheres? So we've increased the pressure from 0.956 to 1.2 atmospheres, and we want to find out what the volume is. This is a before and after problem because you have atmospheres given before, atmospheres given afterwards, and liters only given before. Now you got to find after. So I tell them to do this. Once you've decided what type of problem it is and the formula that you need to use, then extract the information and put it in a form that's independent of the pros. 12.4 liters is how you begin at a pressure of 0.956 atmospheres. And now you're increasing the pressure to 1.2 atmospheres. And this is your unknown. Now that you have those values in their proper place, you can put them in the formula and you know that your calculation will be correct. If you try to extract that information directly from the problem and put it in here, there's a chance that you may put it in the wrong place and get the wrong answer. So let's solve for this unknown. Right? Solve this equation for V2. Put this P2 over here under P1. P1, V1 over P2. Now we can put the values in. P1 is this. V1 is this. And P2 is this. That's the thinking part. All this required thinking. The rest is just number crunching. Once you've got everything where it needs to be, you just crunch the numbers. 0.956, 12.4 times that and divide by 1.2. That should be three significant figures. Volume 2 should be 9.88 liters. Oops. Yeah, that's right. That's correct. There you go. All right, I spent a lot of time solving that one problem just to make the point that it's best to extract the information into a form that's more recognizable before you try to use the formula. All right. You know, one thing we didn't do in here, I mentioned scientists don't like curves. We like straight lines when we can get them. So I don't have a slide on this, but I'm going to show you anyway. I don't think I have a slide on this one. Let me check. No, I'm going to add this one. There's no slide for this one, but I'm going to add this discussion because it's important. Let's clean that up. There we go. All right. So remember, Boyle's law is pressure times volume equals a constant. If we plot that one, all right, I'll do that one again. Pressure, volume, and you need units of measure. Let's see, this is atmospheres and this is liters. Then you get a curve like that. That curve is called a hyperbola. Right? If you remember your math classes, your geometry classes, then you may remember that this shape of the curve is a hyperbola. In other words, this tail would go out to infinity and never touch the axis. This one will go to infinity and never touch that axis. That's characteristic of a hyperbola. Well, if we take this expression here, P times V equals a constant, then what if we divide both sides by volume? We can do that. That's permitted, mathematically speaking. So what does that give us? Well, that cancels volume here, and that gives us K times 1 over V, correct? So we have pressure is equal to K times 1 over V. That is a straight line, right? Y equals mx plus V. Right? This is P. This is K. This is 1 over V, which is our X. And what's B? B is 0. Right now, if we plot that one, against 1 over V. So how would you do that? Well, when you have this data set, pressure, volume, 1 over V is simply the inverse of that value. Divide that into 1. But do it for the units also. This is liters. This would be liters to the minus 1. So the unit of measure here is liters to the minus 1. Okay, now when you plot it, you get a straight line. And the slope of that straight line is K. All right, that we can work with because we understand straight lines. Okay, so now let's go to the next gas law. We're taking these in historical order. In other words, Boyle's law came first because we had the technology to investigate gases relative to their pressure and volume. The next leap forward required a reliable way to measure temperature. Right? And I think we've talked about temperature before, right? We have 3 possible systems. We have degrees C, Celsius, we have degrees F, Fahrenheit, and we have K, which is Kelvin, right? And Kelvin equals degrees C plus 273. I think we talked about that in an earlier chapter. All right, now if we're going to investigate the relationship, between volume and temperature, if we're going to let these vary, then pressure must be constant. Okay, so if we hold pressure and moles constant, we can investigate volume versus temperature, and that's what Charles did. What Charles determined was, and by the way, how do you maintain constant pressure and let the volume change? Well, here's one possibility. You have a cylinder and you have a piston in it that seals the gas off inside, and the piston can move up and down, and then you just put a mass on top of it, like maybe 1 kilogram. So the pressure is always the same, atmospheric pressure plus 1 kilogram. Right? And you measure the volume, right? You have a calibrated cylinder, measure the volume, and you change the temperature. So how do you change the temperature? Well, one way is to seal off your container and then change the temperature around the gas and let it equilibrate until the temperature inside is the same as the temperature outside. Okay? And all you have to do now is measure the temperature in here with your thermometer. Right? Measure the temperature in here, and that's the same temperature as the gas. Okay, so Charles did it with, I think he just did it with air, maybe with some other gases, but I'm not too sure. But what we find out is that the response is as temperature increases, volume increases, right? This is a quotient of two variables. When you have a quotient of two variables equal to a constant, you have a direct proportion. And all you have to do is graph it. I'm the experimenter. I change the temperature. So it goes on the x-axis. And we can measure this in degrees C. And the response is a change in volume, say liters. Okay? And say I pick one gas and I do the experiment and I get a series of points. Like that. That's a straight line with a positive slope. Positive slope means direct proportion. Anytime you have two variables that are in a quotient together equal to a constant, that's a direct proportion. As opposed to Boyle's law, which is a product of two variables equals a constant, that's an inverse proportion. Notice here that if this is 0 degrees, these are negative values on this side. So you can graph that data, but if you try to put that data into this formula, right, negative numbers in temperature, you end up with a negative value for K. It's okay as long as you use positive temperatures, but once you get into the negatives, you're going to get a negative K, and now K is not constant, right? So the only way around that is to find a system of measuring temperatures where all the values of the temperature are positive, always positive. And that's where Kelvin comes in. Lord Kelvin took data like this and extended it out here and said, okay, this is 0K, absolute zero. There's nothing below it. So all the values in K are positive. So whenever you work with Charles' law, you must change the temperature to Kelvin. It's got to be a positive value. Okay. Now the slope of the line depends on the gas. Right? If you have a pure gas of some kind and you conduct this experiment, you'll get a different slope. Right? That's what this graph is showing us. But they're always direct proportion. All right. Positive slope. Okay. So notice if we use Kelvin as our temperature, all the values are positive. So Charles' law came along about 100 years after Boyle. It took that long to perfect the measurement of temperature. And Charles gets credit for the law, but he didn't publish it. Right? In those days, actually coming out of the Middle Ages, scientists would communicate directly with one another. And publication eventually became the way to disseminate information. But even then, some scientists didn't think their work was either publishable, or they didn't want to take the time to do it, or they were insecure about the results. So they'd send their results to fellow scientists working in the same area and get their opinion. Well, I assume Charles did that, and Joseph Louis, I thought his name was Gay-Lussac. Anyway, he actually published the work in the beginning of the 19th century, but he gave Charles credit for it. That's why Charles' name is attached to the law. It wasn't Charles' publication, but it was his work. Okay. Volume and temperature are directly proportional as long as the moles and the pressure are constant. And we could also solve this. We could do it like this. Volume equals K times temperature. And this slope here would give us K. Right? That's a straight line. Y equals mx. As long as the temperature is Kelvin. All right. So we can use the same reasoning here. If we say this is one equal to this one and this one, then we can say those two are equal to each other. V1 over T1 equals V2 over T2. This is before and after. So if you have an experiment like this, and you find that you have volume of the air and the temperature at that volume, then you change the temperature to another value, but you don't have the volume. That's a before and after situation, right? So you would pull the values out. You would write your V1, T1, V2, T2, and be sure and change these to Kelvin, whichever one you have. If there's one unknown in there, then its value will come out as Kelvin, and then you may be asked to change it back to Celsius, which would be just subtract 273 from it. All right, so working this problem out, right, we have V1 is 1.3 liter, T1 is 24.7 plus 273. Now your book might say 273.15. I just used 273 for our purposes. And then V2 is unknown. And then T2 is minus 195 plus 273. Right? And we've solved for V2, and we find now that the volume has decreased to 0.341 liters. All right. And this is an illustration of what happens when you change the temperature. Actually, no, we're in a new law, pardon me. We got a different law now. Okay, so let me erase the board and we'll go to the next law. This is Avogadro's law. Okay. Avogadro's law says if we maintain a constant pressure, okay, and we maintain a constant temperature, then we let these two vary. So if we change the number of moles of gas in a confined space, then the volume will increase proportionally. So volume and moles are in that relationship, right? This is a direct proportion. Increase the number of moles, you increase the volume. Avogadro's law came along in the 19th century. Let's see. The other two, let's go back. I'm curious. All right. Charles did his work in the 18th century. It wasn't published until the beginning of the 19th century. And then, of course, Boyle, mid-17th century, 1600s. Okay. All right. So now we're back to not Charles, but Avogadro. There we go. Okay, so if we plot number of moles of gas against volume, we get a straight line. Okay. Change the number of moles, you get a volume like that. And if we use the same reasoning as before, a before and after situation, then V1 over N1 equals V2 over N2, or as given here, N1 over V1. That's a direct proportion. All right. You will also see Avogadro's law written this way or explained this way. If you have two containers, we can call them spheres or whatever. If they are exactly the same volume, right? Same volume, we maintain the same temperature in each, and we have the same pressure inside the containers, then it must follow that the number of moles in this container equals the number of moles of gas in that container. And it does not matter what the gas is. This is a more useful version of Avogadro's law. Okay, so if we're given this problem where we have 2.45 moles of argon gas occupies a volume of 89.0 liters. So this is comparing two separate gases, right? This problem is before and after. So this would be before, and this would be after we made the change. So before volume is 89.0 liters, okay? And the number of moles before is 2.45 moles. 2.45 moles. Okay? What volume will 2.10 moles of argon occupy under the same conditions? So we're actually going down. And this one is the unknown. So you put those values in here, like that, solve for the new volume, and you find that the volume has decreased 76.3 liters. All right, before we get to the ideal gas law, I want to talk about one other. Before we leave the before and after versions of solving gas equations, I want to introduce you to the combined gas law. All right. Suppose our situation doesn't allow us to hold two of these constant. In other words, they're all varying, or maybe three of them are varying. In order to derive the combined gas law, we're going to start with Boyle's law. Okay. Well, we also know that Charles' law says volume and temperature are proportional. And we know from Avogadro's law that volume and moles are proportional. So now we have a combined gas law. You still, if you know all of these variables have values except for one, then you can solve for that one unknown. Now, if you end up with two variables that are unknown, you can't solve it with one equation. But this is the combined gas law. And notice, if moles are constant and temperature is constant, you have Boyle's law. Okay, so you can use this one to derive the other three laws. All right, now for the ideal gas law. If these are equal to each other, then they're also equal to a constant. So let's just take the one of the combined gas law. Let's say that one is equal to a constant. If you know what this constant is with the correct units, and you know three of these, you can solve for the fourth one. This is not a before and after. This is before after situation. This is a state situation or a state function. In other words, you know what it is right now. You don't know how it got there. That's where we're going with the ideal gas law. All right. So if these are equal to a constant, and let's say we pick the units of measure. The units of measure for pressure, atmospheres. The units of pressure for volume, liters, moles, and K for temperature. That means that the units of measure for this one are liter, atmospheres, per mole, K. Now, if that's the case, then we can give this one a special letter. We call it R. That's the ideal gas equation constant. And we can also calculate what that value is if we know what these values are. Right? If we know that 1 atmosphere pressure and 1 mole of gas at what's the standard temperature for gas is 0 degrees Celsius or 273 K. And we measure the volume of gas under those conditions, we get 22.4 liters. Then we solve this, and that means R equals 0.08206 liter atmospheres per mole K. Right. Now we've got a constant. All we need is to be sure that we use the right units of measure, and if one of them is missing, we can solve for it. All right. Now, you want to be able to tell the difference between a before and after versus a state. The state is going to be easy. You've only got one value for each one of these with one missing. Right? So in this case, an automobile tire is 23 degrees Celsius, 25 liters is filled, 3.18 atmospheres. How many moles of gas? Right? You don't have more than one temperature, more than one volume, more than one pressure. Just one, and one. And you want to know how many moles. If you have the right units of measure here, if you don't, you have to change them. All right, then we can put that into our equation, solve for the number of moles. And we find that under those conditions, that tire has 3.27 moles of gas. Right. This then, you'll more than likely see it written this way. PV equals NRT. And this is the universal or ideal gas equation. Okay. All right, here's another problem. You have a tank that's 304 liters. It contains so many kilograms of helium at 25 degrees. What's the question? What's the pressure? All right. Notice we have kilograms of helium. We don't have moles. So you have to change the kilograms of helium to moles. And we can do that. We use the molar mass of helium. So that's what this part of the equation is doing right here. Notice this is moles, this is moles. We have to change kilograms to grams first. Then we can use the molar mass. 1 mole of helium is 4.003 grams of helium. That gives us moles. Here's our constant. Here's our temperature converted to Kelvin. And here's liters. Now we can solve it for pressure. (114 atmospheres inside that tank. Now, like any of the calculations and problem solutions that we are learning how to do in this course, you're not going to go to bed thinking chemistry and wake up having mastered it all. This doesn't happen subliminally. That's why I give you that review document. It's got lots of problems in it that you solve, and you refine your skill working those problems, right? And the homework that's also given to you through Cengage is another way to master the problem-solving techniques in chemistry. So if you can't do that, then solving problems is going to be a problem, a big problem for you. It takes practice. And remember what I said at the very beginning, your 2 best friends in chemistry, curiosity. You always want to know more, and boredom. If you work those problems, if you work the homework problems and you get bored working them, that means you probably know the solution methodology for that problem pretty well. All right. So let's see, at what temperature does 121 milliliters of CO2 at 27 degrees and 1.05 atmospheres occupy a volume of 293 milliliters at a pressure of 1.4 atmospheres? Okay, so you have volume of your CO2 in milliliters. It must be changed to liters. You have temperature at 27 degrees. It must be changed to Kelvin. You have a pressure of 1.05 atmospheres. Hold on a second. We have 2 volumes, 2 pressures, and 1 temperature. This is a before and after problem. But we have 3 variables here. This problem will be solved best with a combined gas equation. Okay. This is going through. There we go. That's the one you want to use right there. P1V1 over T1 equals P2V2 over T2. So atmospheres, actually, if you use the combined equation, you don't have to change the volume, right? Or you can use any units of pressure you want. The only one that must be in Kelvin is temperature. All right, there's the temperature, 969 K. But we want it in degrees C. So you subtract 273 from it, and the temperature now is 696 degrees Celsius. All right. One more law. This is Dalton's law. John Dalton of partial pressure. Okay. Beginning of the 19th century. What Dalton was saying was, now the scientists were developing ways to separate gases, or how to create pure gases and then put them in mixtures. What Dalton was saying was, if you have a mixture of gases in a container, two or more gases, homogeneous mixture, solution in a container, then if you measure the total pressure of the gases in that container, you are actually measuring a summation of the pressures of each individual gas, all the way out to however many you have. And that doesn't mean moles. This means a number, right? It could be 1,000, it could be 1,000,000, however many gases you have. This total pressure is actually the summation of pressures of all the individual gases in that container. Okay, now, since the pressure, remember the combined gas law, PV over NT, 1111 equals P2V2 over N2 T2. The pressure is affected by the number of particles. So Avogadro's law says that these are related. But when we combine them into this equation, we're also saying that those two are related. Pressure is dependent upon the number of particles in the container. And it doesn't matter what the particles are, right? If we have a total of 8.4 atmospheres on this one with helium in it, 1.75 moles, but in this one we have a mixture where the total moles is 1.75, the mixture could be anything, right? And it could be different gases and different numbers of each gas. The total pressure is 8.4. Well, the ratio of the individual pressures is based upon the number of moles of each gas. One thing about gases is there's a whole lot of room between the particles. The molecules or atoms of gas have lots of room between them. That's why they always make a solution, homogeneous mixture. And why the volume of the individual particles is not very important, because it's so small relative to the distance between them. Most of gas is empty space, right? So that's what we're saying. So the forces among individual particles is not very important either. All right. Excuse me. So here's a practical application of Dalton's partial pressure. I've done this experiment before where you react you conduct a chemical reaction and it produces a gas. And you collect the gas in a device like this. That's water. And you have a graduated cylinder inverted like this. And that cylinder is full of water. You have water in here, and you have water in here. Well, your reaction vessel over here is producing a gas, comes out here, and it goes in like this, right? And bubbles here, and you collect that gas up here. Okay? Now, what is in that space above the water? What's in that space is the gas from the reaction plus water vapor, right? So the pressure inside that space is the addition of the pressure of the gas and the pressure of the water. Okay? But we only want to know how much of the gas from the reaction is in there. So we got to find a way to remove the pressure of the water. Well, fortunately, potassium chlorate is our example here. It decomposes. Potassium chlorate decomposes into potassium chloride and oxygen gas. Let's see, that's going to be 3, 2, 2. So now it's balanced. So we collect the oxygen gas, and if we know how much oxygen gas is over there, then we can do some stoichiometry with the reaction, with the equation. All right. So how do we do that? Well, fortunately, the vapor pressure of water is dependent upon temperature. So we know at any temperature in here, we can find out the pressure of water inside that container. So if we know the temperature, then we can determine a value here, subtract it from the total, and find out the pressure of the gas inside. Okay? So I'm not going to go any further with that, but this is a practical application. Here's another one where we're actually going to solve the problem. So in this problem, next one, here we go. You have 2 flasks. The one on the left is 9-liter capacity at 2 atmospheres, and the one on the right is 3-liter capacity at 3 atmospheres. And all this is taking place at 45 degrees Celsius. Now, this is one case where the temperature doesn't matter. As long as the temperature is the same for both of them, then we can solve the problem. What we want to know is what's the final pressure once we open that valve. When you open that valve, the gases are going to mix, right? So we have this big container here connected to a smaller container here, right? So this one is 9 liters at 2 atmospheres. And this one is 3 atmospheres in 3 liters. Okay. Now let's do qualitative, a semi-qualitative, quantitative assessment. When you open that valve, what's going to happen? Well, the higher pressure here is going to force gas this direction. All right, so we know which way the gas is going to move. What does that say about the final pressure? The final pressure cannot be higher than that, and it cannot be lower than that. So the total pressure is going to be approximately between 2 and 3 atmospheres. Okay, somewhere between those two. Here's how you solve the problem. When you open the valve, consider each side independently of the other. So if we let this one be a vacuum, for the purposes of assessing what happens to this one, we have a before situation here. Pressure 1 equals 2 atmospheres, right? Volume 1 equals 9 liters. Pressure 2 is unknown. Well, what's volume 2? Volume 2 is 9 plus 3, or 12 liters. Okay, now we can solve that using Boyle's law, right? Pressure 2 equals pressure 1, volume 1, divided by volume 2, right? So we have 2 and 9 divided by 12. Right? So this is 18 divided by 12. Let's see. 18 divided by 12 is 3. 6 divided by, it should be 3. I think. Let's try that. 18. No, 1.5, excuse me. 1.5 atmospheres. That's the pressure contributed by this side when we open that valve. Now, let's say this one is a vacuum. And do the same calculation over here. Right? Pressure 2 equals pressure 1, volume 1, and volume 2. Well, the volume 2 is going to be the same, right? 12 liters. What's the pressure 1? Well, the pressure 1 is 3 atmospheres, and the volume 1 is 3 liters. So 9 divided by 12. Is 0.75. Now we have the pressure contributed by this side, the pressure contributed by that side, add them together. Right? Total pressure equals 1.5 plus 0.75, or 2.25 atmospheres. Okay. Is that right? Well, it is between 2 and 3. Yeah. So we used Dalton's law of partial pressures and Boyle's law to solve this problem. Right. That's the left side, gives us a pressure of 1.5. And the right side gives us a pressure of 0.75. Now the total pressure is the sum, and there's your answer. All right, let's see how much more we have to cover. I want to be sure and cover everything. All right. I'm going to need to move along here. We may have to skip this problem and just show it on the slide. 27.4 liters of oxygen gas at 25 degrees and 1.3 atmospheres, and 8.5 liters of helium gas at 25 degrees and 2 atmospheres pumped into a tank with a volume of 5.81 liters at 25 degrees. So the temperature is constant, right? 25 degrees, 25 degrees, 25 degrees. What's the new partial pressure of oxygen? Well, let's see. We put oxygen in there. We put helium in there. All right. We use Boyle's law to find the new pressure of oxygen before and after situation. Right. So the new pressure of oxygen goes from, let's see, 1.3 atmospheres of oxygen to 6.13 atmospheres. And then the pressure of helium goes to 2.93 atmospheres. The total pressure in there is just the combination of the two, 9.06 atmospheres. All right. All right. This is just a review, right, to remind you of what the scientific method does. Well, first of all, what is a law? Remember what a law is. A law simply says this is how the system behaves under these conditions. Makes no attempt to explain why. Right? Some laws are just statements. Some laws are equations. Some are both. However, a theory attempts to explain why something works. So usually why a law works. The law generally comes before the theory. And with a theory, right? Let's see, we don't need this anymore. If you have a law, that just explains what happens. With a theory, you explain why. Why the what? And with a theory, very often we try to create either a physical, a mathematical, or a mental image of what's happening in that theory. We call that a model. Think of a model airplane or a model battleship. Is that an airplane? Is that a battleship? No. It's a representation of those, airplane, battleship. But since we have a model of each, we can change things about it and see how that affects it. Right? That's the advantage of a model based on a theory. We can actually change parts of the model to see what effect that has on the theory. Whereas with a law, if you change something in a law, it doesn't work anymore. Okay, now we're headed to an explanation, a theory of gases that explains why the gas laws work. And that's the kinetic molecular theory of gases. All right. So let's get some what we call postulates. These are assumptions that are required for the theory to work. Get that out of my way. The kinetic molecular theory. Now, the kinetic molecular theory was first developed for gases, but it's since been expanded to include behaviors of liquids and solids as well. But now we're just talking about gases. First of all, gases consist of tiny particles that we can't see, atoms, molecules. the size of the particles, let's see, 1. Right, we have to assume particles. And here, we talk about the size of the particles. The size much, much, much less than the spaces. The spaces between them. So the size of the particle is almost insignificant. The particles are in motion. And they collide with each other and the walls of the container. Okay? That's how we can measure pressure. If these particles were not colliding with the walls of the container, then they wouldn't be colliding with the membrane in our gauge, and we wouldn't be able to measure their pressure. Fourth postulate is no interactions. Except elastic collisions. By that, I mean they behave like billiard balls. In other words, when they strike each other, they just bounce off. No attractions or repulsions as a consequence of their makeup, of their identities. And 5, their temperature in Kelvin is directly proportional to the average kinetic energy of all the particles in the container. So temperature actually is a measure of the average kinetic energy of these particles. All right, that's what I just said. So the implication is that if this is true, and we're measuring both impacts, and we're saying that the temperature is a representation of the kinetic energy, these particles are not insignificant in terms of their mass. Right? So we can calculate the kinetic energy of any one of those particles with this formula. In this case, V is not volume, it's velocity. So the mass times the velocity squared times 1/2 is the kinetic energy of any object anywhere in the universe. What we're also saying is that the pressure will increase as the temperature increases because those particles speed up. And when they strike the walls, they strike with more force because they have more kinetic energy. That is a relationship between pressure and temperature. Now, if the pressure on the gas is constant, then if we heat it up, then we're going to increase the kinetic energy of all the particles in there. They're going to strike the movable piston with more force because they're moving faster, and that causes the volume to increase. That's an explanation of the relationship between volume and temperature. Now, one that we left out was, what's the explanation between pressure and volume? Right? What is pressure? Well, if the volume inside the container actually decreases, right? If this decreases, the pressure goes up. Why? If the temperature is constant, then all the particles in there have the same or average kinetic energy. That hasn't changed, but we are decreasing the area. If you decrease the area, make that smaller, but the forces of each atom are each molecule are the same, then if you have more molecules applying similar force, then the more molecules you have, you increase the force. And if you're decreasing the area and increasing the force, you're increasing the pressure. Right? So decreasing the volume increases the pressure, and that's the kinetic molecular theory explanation. All right. Say you're holding two balloons, one's helium and one's hydrogen. We're going to complete each of the following as either different or the same. All right. Next slide. The pressure of the gas in the two balloons, the pressures are what? If they are the same, same volume, yes, same volume, they will have the same pressure. Right? Because they have exactly the same number of particles inside. At the same temperature, with the same average kinetic energy, applying the same force to the balloon on the inside. All right. The temperatures of the gas in the two balloons are the same. They're in equilibrium with the atmosphere, which is at a given temperature. And that means the volume has to be the same if the temperatures are the same. How about the number of moles? Now we're talking Avogadro's law. Same volume, same temperature, same pressure, exactly the same moles. All right. How about this one? The densities of the gas in the two balloons. Well, if we have the same, what is density? Remember density? Density equals mass per unit volume. Okay. If you have the same number of particles of helium as hydrogen, what's the relationship between the two? Each one of the particles, atoms of helium, is about 4 grams per mole, or 4 atomic mass units. Hydrogen, however, is only 2 atomic mass units per particle. So it has half the mass with the same volume. If it has half the mass with the same volume, then they will not have the same densities. All right. That explains the difference in density. And that also explains the lifting capacity of helium versus hydrogen. Right? Hydrogen has less mass in that volume, has lower density. It has a greater lifting capacity than helium does. Only hydrogen's very dangerous, right? Just ask the survivors of the Hindenburg. Well, that happened so long ago, they're probably all dead now anyway. But the fact of the matter is, the Hindenburg was able to carry more mass because the hydrogen had a higher lifting capacity, as long as you didn't explode. All right. Sketch a graph of pressure versus volume at constant temperature in moles. This is a test to see if you remember what we've studied so far. So what should be the appearance of pressure versus volume? It should be a hyperbola, correct? Right? It should look like that. How about volume versus temperature? Right? Whereas pressure and volume are inversely proportional, volume and temperature are directly proportional. So they should produce a straight line. How about volume versus moles, Avogadro's law? That's also a direct proportion. This is the way the graph should appear. All right. Say we have a balloon with neon in it, and it has twice the volume of the balloon with argon in it. That's what that equation means. The volume of neon balloon is twice the volume of the argon balloon. Right? Now, what's the question? What's the mass ratio of the two? Well, we know that if the volume of neon is twice the volume of the argon, what does that say about the number of moles of each? The moles of neon should be equal to twice the moles of argon. Right? Okay. So if we're looking at the mass, we need the molar mass of each one. Well, the molar mass of this one is about 4 grams per mole. And the molar mass of argon is about 40. Oh, excuse me, neon. No, neon is 20. 20 grams per mole. And argon is 40 grams per mole. Okay? So, if neon has twice as many moles as argon, right? And if this is, take this as 1 unit, equals 40, this one would equal 40. So their mass ratios should be 1 to 1. All right. I just have just a few minutes left. Let me see if I got time to do that. All right. I'm going to run out of time, but I'm going to stay here and finish the lecture. You have a sample of nitrogen gas in a container fitted with a piston that maintains a pressure of 6 atmospheres. Initially, the gas is at 45 degrees Celsius and a volume of 6 liters. You then cool the gas sample, right? What's going to happen when you cool it? The volume of the gas is going to decrease. Why? Because you're decreasing the kinetic energy of all the particles in the gas. They're impacting the piston with less force. So in order to balance, the volume decreases until the number of impacts from underneath in the gas are equilibrated again, are equal to the given number of force of the external force. So the volume of the gas will decrease until you reach an equilibrium again. Right? If we actually cool to 15 degrees, what gas law would we use? Volume and temperature is Charles' law. Right? And if we use Charles' law with the information that's given in the previous slide, we find out that now the volume is 5.43 liters rather than 6 liters. So the volume actually has decreased. So what do we mean by the molar volume of a gas? The molar volume of a gas is the volume occupied by 1 mole of gas at standard temperature and pressure. And if we solve it, if we know what R is, 0.08206 liter atmospheres per mole K, and we substitute 1 mole, 273 K, and 1 atmosphere pressure, we find that the molar volume of a gas is 22.4 liters. Now, when I showed you the universal or the ideal gas equation before, I just gave you 22.4 liters. But if we know what the R constant is, we can calculate that value. So it's just go at the problem one way, go at it a different way. Now, how about gas stoichiometry? Well, we've approached stoichiometry from mass of reactants and we've approached it from volume of molar solutions. Now, this is stoichiometry. Now we want to look at effective gases. Either as reactants or products. So if we have a sample of oxygen gas, a volume of 2.5 liters at standard temperature and pressure, how many grams of oxygen are present? Right. This is the beginning of stoichiometric calculations. So 2.5 liters of oxygen. We're going to convert that to, right, we have the molar mass here of gas, 22.4 liters per 1 mole. We can calculate the number of moles of oxygen and then convert that using the molar mass of oxygen to 3.57 grams. Or you can use the universal gas equation, right? Put in the values for atmospheres, liters, there's the moles unknown, there's your R constant, there's the value of temperature, and calculate the moles, and we should get the number of moles, and then we can convert that number of moles to mass, right? Either way works. Now, how about this reaction, right? We've got zinc plus hydrochloric acid yields zinc chloride or zinc 2 chloride in aqueous solution plus hydrogen gas. All right, so what's the question? Well, if you have 15 grams of solid zinc reacting with 100 milliliters of 4 molar hydrochloric acid, what volume of hydrogen gas is produced at 25 degrees and 1 atmosphere? All right, well, there are our choices. This is what I would call a complete stoichiometry problem with gases. So here's our balanced equation, right? That's the first thing we would have done, is balance the equation. Right? Zinc 2 chloride. Right? And the equation's already balanced for us. That's kind. Plus, oh, not oxygen, hydrogen. There we go. 15 grams here of zinc. And we have 100 milliliters of 4 molar. 100 milliliters of 4 molar hydrochloric acid. And the conditions are 25 degrees and 1 atmosphere. So 25 degrees C and 1 atmosphere. And the question is, how many liters of gas are produced? So the volume is what we're after. How many liters? Okay. Remember, when you have 2 reactants, exact amounts of 2 reactants given, you got to find out which one is limiting. So that's where we're headed next. So if we convert 15 grams of zinc to moles, remember, you can't move anywhere in this equation without moles. So this is going to have grams here, moles there, and that's 65.38. 65.38 grams per mole gives you 0.2294. 0.294 moles of zinc. Okay. You know what? We've skipped a step. No. We're determining how many moles of hydrogen could be produced if all of this were consumed. Right, that's the first step. So we have zinc versus hydrogen, and we have one there and one there. So that's equal to 0.2294 moles of hydrogen. That's what we would produce with all of the zinc. Now, how much hydrogen would be produced with the hydrochloric acid? So we have 1/10 liter of hydrochloric acid times 4 molar. Right? Remember, molarity equals moles per unit volume. So moles equals molarity times volume. That's what we've done here. Volume times molarity. And that's 0.400 moles of HCl. Right? And then we take that and convert that to hydrogen. HCl here, hydrogen there. This is 1, this is 2. So that's 0.200 moles of hydrogen. So which one is limiting? This one is limiting. That means that's the number of moles of hydrogen that's produced. Now convert to volume. Well, we know the moles. We're looking for volume. Excuse me. That's pressure. There we go. So we have number of moles, 0.2, 0.08206. Temperature, plus 273. All right, so we have 298 K divided by pressure. What's the pressure? 1 atmosphere. All right, so what's the volume? Volume is 4.89 liters. Under those conditions. Okay? That's a stoichiometry problem using mass relation, solution, concentration and volume, and gas. All three together in one problem. Let's see. Okay, this is the discussion that I had earlier. How do you convert the Boyle's law curve into a straight line? You take volume and calculate the inverse, and then you plot pressure against the inverse of volume, and you get a straight line. Oops, that's not what I wanted. And that's the end of our discussion. Okay, so the next time we meet, let's see. We've introduced the topic. Next Tuesday, April 2nd, I'll start the review using the review document. If we have time, which we probably will, we'll finish the review that day. And then in your syllabus, the schedule says that we have a review on Thursday. So that Thursday, following next Tuesday, I'll open Zoom and be in class so that we can either finish the review if needed, or I can be here to answer questions. And I'll stay here for maybe a half hour. If there's nobody here and nobody zoomed in, I'll stay for a half hour just to be sure that nobody's going to show up. And if nobody shows up, then I'll close the class after about a half hour. Okay, that's it for today. Yeah, it's not going to let me. Did I stop share? Let's see. No, it's not responding. All right, I might have to reboot the computer.